Welcome back, everyone. Ready for another deep dive. Today we're taking on Lie algebra.
Sounds intimidating, right?
A little bit, I have to admit.
But it's really fascinating once you get into it.
We're going to try to make it as clear as possible, of course.
Definitely.
So to guide us today, we've got excerpts from Lie algebras, interactions and rules in vector space, and of course, the always reliable Wikipedia page on Lie algebra.
Both great sources.
Now, before we get lost in the weeds, can you give us a high-level view? What exactly is Lie algebra?
Well, think of it as a mathematical framework for describing how things interact and change.
Okay, I'm intrigued. Our first source uses the analogy of a box full of toy cars.
Right, it's a helpful visualization. The box itself represents a vector space.
And those toy cars are the vectors.
Exactly. But a Lie algebra doesn't just stop at vectors. It adds something called a Lie bracket.
And what's that exactly?
The Lie bracket tells you what happens when two of those vectors, or toy cars, interact.
So it's not just about the vectors themselves, but how they, combine or influence each other?
Precisely. It captures that interaction.
Interesting.
And it's denoted by this notation, x, y, where x and y are the vectors.
Okay, I see. But it's not always simple addition, right?
Not necessarily. The outcome really depends on the specific rules of the Lie algebra.
Each Lie algebra has its own set of rules, then.
You got it.
Our source mentions a key property of the Lie bracket. It's alternating. Can you unpack that a bit?
Sure. In our toy car analogy, it means a car can't collide with itself.
Makes sense.
Mathematically, this translates to the Lie bracket of a vector with itself always being 0.
So x equals 0.
You got it.
Okay, got it. But things get a bit more complex with the Jacobi identity, right?
Yeah, the Jacobi identity is all about consistency when you have multiple interactions happening. Imagine 3 cars colliding. The Jacobi identity says the final outcome is the same no matter what order they collide in.
So even if the individual collisions are different, the overall result is predictable.
Exactly. That predictability is essential in Lie algebra.
So we've got this toy car analogy, but our Wikipedia source gives a more formal definition.
Right. Formally, a Lie algebra is a vector space denoted as G over a field F, and it includes this binary operation, the Lie bracket.
Okay.
But there are rules. The Lie bracket has to satisfy bilinearity, that alternating property we talk about, and of course the Jacobi identity.
So those 3 properties are kind of like the ground rules.
Yeah, you could say that.
They create the structure of a Lie algebra.
Exactly. They're what make Lie algebra so powerful.
All right, let's move from the abstract to some concrete examples. What are some types of Lie algebras?
Well, there's the abelian Lie algebra. It's the simplest one.
Simple in what way?
The Lie bracket is always 0. No collisions between those toy cars.
So it's like a parking lot full of cars that never move.
It's a very peaceful one. Haha.
I like it. But there's got to be more exciting stuff.
Of course. We have matrix Lie algebras for evidence.
Ah, matrices. Always a good time.
Instead of cars, we're dealing with matrices here.
And matrices represent transformations, right?
Exactly.
So in this context, what's the Lie bracket all about?
It's defined using the commutator of matrices.
The commutator. Didn't that measure how much 2 transformations don't commute?
Exactly. It tells you how much the order of operations matters.
Right. Because sometimes the order you do things in makes a big difference.
Especially with matrices. And the commutator quantifies that difference.
So the Lie bracket in a matrix Lie algebra is all about how the order of transformations changes things.
You got it.
Okay. Are there any specific matrix Lie algebras we should know about?
Yeah, one important one is the general linear Lie algebra.
Never heard of it.
It's denoted as GLFN, F, and deals with NXN matrices.
Sounds complicated.
It is, but it has a close connection to the general linear group, which is denoted GLMNF.
Which is?
The group of invertible NXN matrices. It's a fascinating connection between Lie algebras and group theory, actually.
Okay. So Lie algebras can tell us something about groups, too.
Exactly. It highlights how interconnected different areas of math can be.
So Lie algebras are connected to group theory, huh? I'm starting to see how deep this rabbit hole goes.
Oh yeah, we've barely scratched the surface.
Before we go any further, though, our sources also talk about classifying different types of Lie algebras.
Right, it's like categorizing them based on their properties.
So instead of just talking about Lie algebra in general, we can get specific.
Exactly, and by understanding those classifications, we can better understand their relationships and how they behave.
Makes sense. The outline mentions solvable and nilpotent Lie algebras. What's the difference?
Well, both of them deal with how certain operations within the Lie algebra sort of become trivial when you repeat them.
Trivial, like they simplify down to something basic.
Exactly. You could almost think of it like how quickly our toy car system settles down.
Okay, I'm following.
So in a solvable Lie algebra, there's a specific sequence of operations called the derived series, and eventually it leads to 0.
So it's like repeatedly applying the rules until everything stops moving.
Pretty much. It's all about how predictable that settling down process is.
And nilpotent Lie algebras, are they similar?
Yeah, they're related. In a nilpotent Lie algebra, a different sequence, called the lower central series, reaches zero.
Another series. Is that like a stricter condition than being solvable?
You got it. The system settles down even faster, you could say.
Okay, so solvable and nilpotent are all about things calming down over time.
Right.
What about simple and semisimple Lie algebras then? What makes them special?
Well, those are considered the fundamental building blocks, like the prime numbers of Lie algebras.
Building blocks.
Yeah, a simple Lie algebra can't be broken down into smaller parts that make sense in this context.
And semisimple, I'm guessing that means it's made up of multiple simple ones?
Exactly. It's basically a combination of simple Lie algebras, like putting together different atoms to create a molecule.
Ah, that's a good analogy.
Classifying Lie algebras this way is incredibly helpful for understanding the bigger picture.
I can see how it would reveal the relationships between them.
Absolutely.
Okay, we also need to talk about Lie groups. How do they fit into all of this?
Ah, yes. Lie groups. They're deeply connected to Lie algebras.
In what way?
Well, Lie groups are a bit tricky to explain simply. They're groups which have an algebraic structure, but they're also smooth manifolds.
Manifolds, like geometric shapes.
Kind of. They're spaces that can be smoothly deformed, like a rubber sheet.
Okay, that's a bit abstract.
It is, but the important thing is the connection. Every Lie group has a corresponding Lie algebra.
So for every one of those twisty, bendy manifolds, there's a Lie algebra that goes with it.
Exactly. And for finite dimensional Lie algebras, the connection is even stronger. You can go back and forth between them.
Interesting. So by understanding one, you gain insights into the other.
Exactly. Lie algebras are often easier to work with mathematically, so they can provide valuable information about the Lie group they correspond to.
Like a simplified model of something more complex.
Perfect analogy. And this relationship has really important implications in fields like physics and engineering, especially when dealing with symmetry and transformations.
I'm starting to see how this all ties together.
It all comes back to that idea of understanding how things change and interact.
This has been incredibly insightful. I'm eager to see how these abstract concepts actually play out in the real world. Okay, so we've talked a lot about the theory behind Lie algebras, all these different types and classifications, but I'm really curious about the practical side of things.
Yeah, the applications are really where it gets exciting.
Our outline mentions quantum mechanics, especially when it comes to angular momentum and spin.
Right. Well, remember how we talked about commutation relations, how the order of operations matters?
Yeah.
Well, in quantum mechanics, the commutation relations between those angular momentum operators, they actually form a Lie algebra.
So we're using Lie algebra to describe how particles rotate at the quantum level.
Exactly. It helps us understand those fundamental properties of particles.
And it's not just single particles, right?
No, Lie algebras are also crucial for understanding symmetry groups in particle physics.
Symmetry seems to be a recurring theme here.
It is. Symmetry is fundamental to physics, and Lie algebras give us the tools to analyze and use it. They help us classify particles, understand their interactions, even describe the fundamental forces of nature.
Wow. So from these abstract mathematical concepts, we're getting insights into the building blocks of the universe.
Pretty amazing, right?
It is. But what about applications outside of physics? What else can Lie algebras do?
Oh, tons of stuff. They're used in engineering, especially in control theory and robotics.
Oh, robotics.
Yeah, like imagine you're designing a robotic arm that needs to move precisely in 3 dimensions.
Sounds like a complex control problem.
It is, but the robotic arm's movements can be described by a Lie group, and its corresponding Lie algebra gives us the tools to actually control it.
So we're using the rule book of the Lie algebra to guide the robot's action.
Exactly. It's all about understanding those underlying mathematical structures to solve real-world problems.
Fascinating. So Lie algebra is helping us build more sophisticated robots.
Definitely. But it doesn't stop there. Lie algebras have applications in all sorts of fields. Computer graphics, fluid dynamics, even financial modeling.
Wow, it's incredible how one mathematical concept could be so versatile.
That's the beauty, abstract math. It often reveals hidden connections and underlying patterns that we wouldn't see otherwise.
So as we wrap up our deep dive into Lie algebra, what's one key takeaway you want our listeners to think about?
I hope they see that even these seemingly abstract mathematical ideas can have a real impact on the world around us. Math isn't just about equations, it's about understanding the structure and patterns of the universe.
Well said. And that concludes our deep dive into Lie algebra. We've gone from toy cars to the fundamental forces of nature, and I hope you've all gained a new appreciation for this fascinating area of mathematics. Until next time, keep exploring the world of math and all the wonders it holds.